So good evening, everyone. So this is the presentation for SCL MTH3202. And my name is Tan Chai Fang with metric number 206493.
Hello everyone, my name is Maria Mohanjeka, matrix number 207269.
Good evening, everyone. My name is Flo Share with metric number 206890.
My name is Nurul Najwa Fatiha binti Abdul Hadi with metric number 207267. So for task 1, the question is verify that G equals to 2 power of m times 3 power of n, which m n are integers, is a group with respect to multiplication. So we have to do 3 steps. The first step, you need to let A equals to the equation, which is 2 power of m times 3 power of n, and then let the B is the opposite of the power, which is 2 power of n times 3 power of m, and then we multiply the A times B, and then equals to 2 power of m times 3 power of n times 2 power of n times 3 power of m in the bracket, and then we got and then we need to simplify. We get 2 times 3 power of m plus n, and then we let k equals to m plus n. For k is integers lah, so G is closed. For the second step, we need to find the inverse. We can let A inverse or B inverse. So I choose A power of -1, which is the inverse, equals to 2 power of m times 3 power of n in the bracket, power of -1. And then we got the integers for G. And the next step is the last step. Next slide. Okay, this one is AB equals to BA, which is need to find the what is this called? Equality. Okay, which is even though we times A first or the B first, we need to we have to find the similarity for the answer. So AB times equals to BA, and then we simplify it again, and then at the fourth row, we let E in the left. So the left one, which is 2 power of m plus n times 3 power of m plus n, we bring it to the right. When we bring it, will be 1 over, which is power of -1. Okay, so E equals to 2m plus n times 3 power of m plus n in the bracket, and then 2m plus n times 3m plus n in the bracket of -1, which is 1 over lah. Okay, and then the positive one, which is 2 power of m plus n times 3 power of m plus n, power of +1. Okay, the left one in the right side, we bring it to the left. So we just ignore the E, we let E equals to 1. So when we bring to the left side, it will be 1 over, which is inverse also, power of -1. And then we can see the similarity between right and left, which is an inverse. Okay, and then we simplify it again. We got 2 times 3 power of -m minus n. Also the same with the right. And then I just wanted to bring out the negative. So we got 2 times 3 power of negative in the bracket m plus n. So we can see the inverse of A, which is a power of -1, and also the inverse of B, which is B power of -1 in G, are commutative. So from the first, second, and the third steps, it is verified that G equals to 2 power of m times 3 power of n, which m and are integers with respect to 3 steps shown. All right. Okay. So next task 2.
Okay, so for task 2 is to prove that if G is a group and AB is also the element of G, then OA inverse BA should be equal to OB. So since G is a group and G is associative, and then so OA inverse BA is equal to OA inverse AB, and A inverse A is become the identity. So finally we can get OEB is equal to OB, which is proof. So for the second question is we have to prove that OAB is equal to OBA. So from the proving of task 1, we know that G is also commutative. And then we can go to OAB is actually equal to O upper bracket AB and then OBA. So finally we can get the answer, which is OBA. So proof. So for next, task 3. Okay, task 3 is to prove the theorem 7.1.10, which is suppose that GH are element of a group G, prove that the equation XG has the unique solution X equal to HG inverse. So from the question XG is equal to H. So by using the right cancellation law, we put G inverse for both sides, and then G inverse is become identity, which XE is equal to HG inverse, and then XE is equal to X, so X is equal to X is equal to HG inverse. So then S is a solution of XG equal to H, and also suppose that Y also a solution of YG equal to H. So we can know that XG equal to YG. So from the right cancellation law, so we can know that X is actually equal to Y, and it shows that the solution is unique. So that's all for task 3.
So for task 4, assume that G is a group with operation, binary operation, and that A is element of G. Let function C is equal to X element of G and A star X equal to X star A. Then prove that C is a subgroup of G. So the answer is, from the question, we already know that the G is a group. So the C is element of G, and the C is not equal to the null set. By theorem 7.3.2, the first step is if A star X is equal to X star A is element of C, and also the B star Y is equal to Y star B is element of C, then the A star B is element of C, so that the C is closed. Then the next step is the A star, the inverse of X is equal to the inverse of X is star A is element of C, so that there is axis and inverse of every X is element of C. Thus, the inverse of X is also element of C. That's all for task 4.
All right, I'll be explaining task 5 now. So the question states that let G equals to Z12 and H equals to cyclic group 4. Find the right cosets of H in G. So when Z12 is equals to G12, which starts from the number 0 all the way to 11 as 12 digits. And H is the cyclic group 4 under class 4. For addition operation, H is equals to cyclic group 4, whereby 4 is which is equals to 4n in n. That means it can be -8, -4, 0, 4, 8, 12, 16, and negative and positive in the cyclic group 4. So H in the class 4, which means cyclic group 4 in class 4 means 4, 8, and 0, which exists in the group G. So using Lagrange theorem, G has 12, whereas H only has 3, which is the digits. So G has 12 digits and H only has 3, which is the 4, 8, and 0. So Lagrange theorem states that digits of G divided by digits of H, which equals to 4. Now the other method is H plus class 0 equals to H, because 4, 8, and 0 plus 0 stays the same. And we continued this with 1, 2, 3, and 4, where we plus all the way. We showed 4 to state that it will repeat itself, whereby there will be the digits 8, 0, and 4, which is 4, 8, and 0, just different positions, which equals to still H. So the right cosets of H in G is equals to H plus 1, H plus 2 and H plus 3, whereby 1, 2, and 3 are each classes. And that is all for task 5. Thank you. Now I will talk about the reflection. So in our team, this SEL has helped us to look at the properties in detail and compare them with other groups. So we discuss them with each other and make sure we look at the details and everything. This also allows us to research and search deep, to dig deeper and explore more about the Lagrange theorem, subgroup, order of elements, and the order of groups. So we learn these things in a much deeper level and we try to understand them in a different method. This also engages with the mathematical theorem to invoke a deeper understanding of the contents needed to learn, for us to learn in the future of our course. And I think that is all from me. And thank you. Thank you.